Alright, what's up lads? So I'm going to go through this past paper, the November 2021 past paper for physics, and I'm going to go through the whole thing step by step. Okay, so we'll start off with the multiple choice questions. And I'll show you my method of solving these and some general tips along the way. So we can start off with question 1, multiple choice. So when you consider the statement below, the perpendicular force exerted by a surface on an object in contact with the surface. Which one of the following forces is defined by the statement above? So it's a perpendicular force exerted by a surface on an object in contact with the surface. So if I had an object, let's say, on a surface, it's a force going up which is perpendicular to the surface. And it doesn't matter what the angle of the surface is as long as it's always perpendicular like so. So this is actually normal force. And that's something you can study. There's not much tips I can give for that kind of question. Next up, we got two balls of masses m and 2m are dropped simultaneously from the same height above the ground. We must ignore air resistance. When the balls strike the ground, which one of the following physical quantities will be the same for both balls? So whenever you do multiple choice, there's always one obviously wrong question, and that's A. It can't be A. Because why? They already told us the masses are different. So they can't be the same weight. Because remember, weight is equal to mass times gravity. It's definitely not A. What else is it not? It can't be momentum. Because P equals mv, and we know the mass changes. And it also can't be kinetic energy. Because, again, kinetic energy has mass in its equation. So the only possible thing it could be is B. So look at that. We went from a 25% chance of getting every question right to a 100% chance by eliminating the obviously wrong questions. So it's definitely B. Alright, next up we got the graph below shows how the momentum P of an object changes with time t. So momentum's increasing, and then slowly starts to decrease, becomes negative, which means it changes direction over here. And there it goes back to the other direction. Alright, so during which one of the following time intervals, measured in seconds, is the magnitude of the net force acting on the object the greatest? So if we take a look at our equation for impulse, right? We know that F net delta t equals delta p. And we want to find what the net force would be. So F net is equal to delta p over delta t. Now let's relate this to our graph. What is P? P is the y-axis. And what is delta t? Delta t is the x-axis. Which means that F net is just the gradient. So we're looking for the greatest magnitude of F net, which means we're looking for the steepest gradient. And that would be between 0.3 and 4. Because if you thought it's between 0 and 1, that won't be right. Because look, it's going 0 to 1, but it's only increasing by 20 units. Yeah, it's going the same length, 3 to 4, 1 unit, but it's increasing by minus 10 to 20, which is 30 units. So it's a much steeper incline there. So it's definitely D, 0.3 to 4. The next question, a ball is dropped from a height above a floor, and the ball makes an elastic collision with the floor at time t0, and bounces vertically upwards. Ignore air resistance. Which one of the following graphs shows how the total mechanical energy, EM, of the ball changes with time? So we know that the ball is dropped from a height above the floor, makes an elastic collision with the floor, which means kinetic energy is conserved, so it's going to bounce to the exact same height it was before. And it bounces vertically upwards, and there's no air resistance. We're looking at mechanical energy. So we know that when there's no resistance or anything, we can apply the law of the conservation of mechanical energy. What does that mean? It means that mechanical energy stays constant all the time. It means it's not this, it's not that, it's not that. It has to say the same. It means it must be B. So one straight line is a constant value on a graph. Next question, 1.5. Consider the two spectrum diagrams below. Diagram 1, we've got a line here near the blue spectrum and then one further down to the red. Diagram 2, it's the same lines, right? But we can see it shifted slightly towards the red side of the spectrum, which means a red shift occurred, which means that this object's moving away from Earth. So diagram 1 represents the spectrum of an element in a laboratory on Earth, and diagram 2 represents the spectrum of the same element from a distant star, as observed from Earth. So which one of the following can be deduced from the spectrum above? Stars moving towards Earth? Nope. Stars at rest? Nope. Stars moving away from Earth? Yep. Because it's being red shifted. Red going longer wavelengths is moving away. Diagram below shows the field lines for the combined electric field due to two small charges, spheres P and Q. So they're asking which one of the following combinations below correctly shows the polarity of spheres P and Q. Alright, so it goes out of positive and into negative. So the charges are going into Q, which means Q must be negative. It's going out of P, which means it must be positive. So it's definitely this one. And also your elimination, B is completely wrong because they can't both be negative. Then it would look something like this. The spheres would move away from each other. Two identical spheres, P and Q, carry charges of plus Q and minus 2Q respectively. Sphere P exerts an electrostatic force of magnitude F on sphere Q. Which one of the following represents the magnitude of the electrostatic force exerted on sphere P by sphere Q? Alright, this one we're going to have to take a look at Newton's third law. Every object attracts another object with a force. You're going to have to take a look at Newton's third law, which is that each force has an equal and opposite force, basically. So it means that for P and Q, it gives us plus Q minus 2Q. We can completely ignore this, alright? So sphere P and Q gives us F. So what would the magnitude be of the one on the other way around? It would still be F. So the answer for 1.7 is B. That's just Newton's third law. In the circuit diagram shown below, all resistors are identical. Ignore the internal resistance of the cell. So we don't have to account for any internal resistance, and we know that all these resistors are the same. So which voltmeter will have the highest reading when switch S is closed? Follow would be A, V1. The reason is, what does a voltmeter read? It reads potential difference. So if we're looking for the highest voltmeter reading, we're looking for the highest potential difference, which means that we want the difference of a voltage or energy, another way to put it, from this point before the resistor or before the voltmeter to that point afterwards to be the greatest. Over here we have voltmeters in parallel, which will have the least resistance, which would cause the least amount of change in voltage. Okay? Which means that here, in series, we've got a resistor, which gives you the greatest resistance possible. Which means the energy here is much higher than energy there, giving you a higher reading on your V1. That's a nice way to think about it, the total energy difference. In which one of the following electrical machines is electrical energy converted to mechanical energy? So we're putting in power and we're getting out motion. So motor motion, DC motor is your answer. Alright. Next up, we have which one of the following combinations correctly links an emission spectrum and an absorption spectrum to the energy transitions of an electron in an atom. So emission, we're emitting something, which means we're going from something to something less. And absorption, we're going from something less to something more. We're gaining. So it's got to be D, from high to low energy levels and from low to high. Alright, let's get on to the fun stuff. Question 2, my favorite. And that was not sarcasm. I know some people struggle with question 2, but I'll show you how it can be actually very easy. Let me put a grid. So, let's read the question. A 20 kilogram block is placed on a rough surface at an incline at 30 degrees to the horizontal, and a constant F acting parallel to the surface is applied on the block so that the block moves up the incline at a constant velocity of 2 meters per second. Refer to the diagram below, and they let us know what the frictional force is on the block, which is 18 newtons. So we need to state Newton's first law in words. Let me try to think. An object in motion an object at rest or in motion has a tendency to stay in its state of rest or motion unless an unbalanced force acts upon it. Okay, that's it. So we know that the acceleration in the system is 0 right now because it's got a constant velocity of 2 meters. In order to have a constant velocity, we are not accelerating. And the next question here is we need to quickly draw a free body diagram for the block. So free body diagrams, easy 4 marks. All you're going to do is you're going to draw your dot. Then you got your, whenever it's on an inclined plane, what you want to do is you want to draw your plane like so. Label your angles. This is 30 degrees. Alright, it's got a force going straight up from the plane. Force F. Now let's think about what other forces are acting on it. We've got a normal force going up. This is F, this is normal. And remember, normal is perpendicular. Then let's think what else. We've got friction pulling down. So that's friction. I'm going to call it Fk for kinetic friction. And let's not forget about the gravitational forces. So when it comes to gravity, you can either draw one line straight down for Fg, or you can split it up into components, Fg perpendicular and Fg parallel. Don't do both. So don't draw your line straight down and then split it into components. Either do components or the total force itself. I like doing components. So there's Fg parallel, which goes down the slope, and Fg perpendicular, which is perpendicular to the surface. You should draw a key. I'm too lazy to do a key. We need to calculate the magnitude of force F. Okay, 2.3, calculate the magnitude of force F. Always use F net equals ma, my favorite equation. Okay, so we know that F net, if we break it up, is going to be that force F. We're going to take away that friction and the Fg parallel. Now ma, that's going to be 20 times 0 because it's not accelerating, it's at a constant velocity, so that's just 0. So the force itself is equal to your frictional force plus your Fg parallel. So kinetic friction they actually told us was 18 newtons, and Fg parallel is going to be Fg sine theta. Now, Fg sine theta, so that's going to, Fg is the mass of the object, which is 20 kilograms times 9.8 gravitational acceleration, and sine theta is the angle of the slope, which is 30 degrees. So our answer there will give you a nice number of 116 newtons. Okay. Next up, they let us know that force F is removed when the block reaches point X over here at the top. Okay? So force F is removed when the block reaches point X on the surface. The block continues to move up the surface and comes to rest momentarily at point Y. Assume that the kinetic frictional force acting on the block remains at 18 newtons as it moves from point X to point Y. And you now write down the total net force acting on the block as it moves from X to Y. So that's going to simply equal exactly what we got here. It's going to be 116 newtons. Reason is, it was balanced, right? So it meant that the force is equal to the friction plus the Fg parallel. Now we got rid of that, but it doesn't change the value of this part of the equation. So I'm just going to write that down. It's going to be 116 newtons. So 2.5, calculate the distance between points X and Y. It didn't tell us how we should do this, which means we can use any method available to us. I'm going to use, what do I want to use? I'm going to use W net equals delta EK. Yeah, I think so. That's what I'm going to do. I'm going to say W net equal to change in kinetic, oh wait, I don't want to do that. I don't know this. Oh, I do know the speed. What's wrong with me? Okay, yeah, that's what I'm going to do. W net equals delta EK. This is a nice equation to use. It's nice and quick. So we got to take a look at the work done in total, which is going to be the frictional force, which is 18 newtons times delta X cos theta, which is going to be cos of 180, moving opposite direction of motion, plus Fg parallel, which is 20 times 9.8 times sine of 30, and then remember delta X cos 180. Alright, so that's the W net side. This is work done by friction, and that is work done by gravity. Right, we'll get rid of that. And then this is going to equal to our change in kinetic energy, which is a half times the mass of the object was 20 kilograms. V final squared, that's going to be 0 because we come to a rest. And then, yep, it does come to a rest, 0 squared. And then the initial velocity was a constant 2 meters per second. Just remember that this 2 only applies, or the squared only applies to the 2, does not apply to that sign. So if we quickly solve this equation, what I'm going to head and do is write the values. It's going to be negative 18 delta X plus, let's see, what is 20 times 9.8 times sine of 30 is 98, so it's actually going to be negative because of the cos 180. So negative 98 delta x is equal to a half times 20 into negative 4. Alright, so minus 18 minus 98 is negative 116 delta x. And a half times 20 is 10 times negative 4 is negative 40. So delta x is going to equal to negative 40 divided by negative 116, which is 0.345 meters. So I'm just going to let you know what other options could have been. So you could have calculated the new acceleration using F net equals ma, and then you could have substituted that into any of the equations of motion questions. You could have even used impulse, but that's like takes long. So you could have used impulse, got the time it takes for it to stop, and then substituted that into the equations of motion. But I honestly think that my method here, W net equals delta ek, is the quickest way to do it. Most definitely. Okay. So, easy 20 marks, am I right? It's actually 16. Alright, next question. Balloon questions, my favorite. These can be difficult. So, they tell us that a hot air balloon is moving upwards at a constant unknown speed. It's important. Is the hot air balloon in free fall? Choose from yes or no. Well, it's going to be no. Okay, remember, for free fall to occur, the only force acting on an object while in motion is gravity. And if it's moving upwards, it can't be the only force. There's some lift occurring. Right now we've been given some extra information at the bottom. When the balloon is 200 meters above the ground, a small stone A is dropped from the balloon. See the diagram above. Another small stone B is dropped 5 seconds later on the balloon, while the balloon is still moving upwards at a constant velocity. Stone A strikes the ground at a speed of 62.68 meters per second. So we're going to ignore air resistance. That's great. Makes life a lot easier. Calculate the speed of the hot air balloon. So how are we going to do this? It's like all the information's about the ball. We don't know anything about the hot air balloon. So how do we get the speed of the hot air? It's very important to know. Whenever you throw something out of anything that's moving, or just drop something out of anything that's moving, the speed at which it's dropped, that initial velocity, is going to equal the velocity of the balloon. So, V initial of the ball is going to equal to that velocity of balloon. You're essentially giving that ball the balloon speed because you're traveling up with the ball at the same time. Even though you drop it, it still has that velocity from what just happened before. So that's how we're going to calculate the velocity of the balloon. We're going to calculate the initial velocity of the ball using the given information. So let's take a look at what we know. We've got a displacement. We've got the time at which, the speed at which it strikes the ball. And that seems to be it. But a better way to go about this is okay, I've found the perfect equation. So let's take a look here. We write down what we know. We know our final velocity, which is 62.68. We know the displacement the ball traveled is 200 meters. We know our acceleration is 9.8. And we also know that's it. Okay, that's all we know. What do we want to know? We want to know the initial velocity of the ball. That is unknown. So we look at our formula sheet and we find the equation that we need to find that has the variables we want to get and the variable we don't know yet. Nothing else, okay? So the perfect equation for us to use is Vf squared is equal to Vi squared plus 2a delta y. And let me just mention that I'm going to take downwards as positive. So before you start the question, always say what you're going to take as positive. I like doing downwards if the majority of the movement is down. In this case, it's falling downwards, so I'm going to take downwards as positive. And stick with that. Do not change the equation. Confuse the markers, you make them upset. Stick to downwards as positive throughout the whole question. Alright, now we substitute in values. So this is 62. Whoops. So that's 62,68 all squared. V initial is what we're solving for. 2, 9.8, and then delta y is 200. So now we bring over the 2. By the way, if you have a calculator, silver calculator, that the Casio 991ZA Plus or the newer version of it, I highly recommend you use the solve function. It's so much quicker than having to manually solve the equation, because this is physics. They don't actually mark your maths. All they mark is your substitution and your answer. So that's going to be squared minus 2 times 9.8, 200. But I'll show the maths just for the people who don't have access to that. So we're going to get a V initial squared of 8,7824, and then that's Vi squared. Then we square root that to get Vi to be 2.96 meters per second. It's important to distinguish the direction, because I square rooted this number, we get both plus minus answers, and the calculator will give you the positive version, right? But we know that it's actually moving downwards. Oh, sorry, it's moving upwards, which means, and I took downwards as positive, so I must distinguish the direction as being upwards. Alrighty, next question. We need to now find the time it takes for stone A to strike the ground. Alright, that would be pretty easy to do, because we've just calculated the V initial, which means we can use the very first equation. Vf is equal to Vi plus A delta t. That's what we can use for this question. It's 3.2.2. There. This is 3.2.1. So we know Vf now, we know Vi, and we know A, and we can calculate delta t. So V final is 62.68. The initial, this is what I mean about distinguishing the upwards. I'm going to put negative 2.96, because down is positive, and that's going upwards, which means I must denote that as being negative. If you don't do that, you're going to get a wrong answer. So acceleration 9.8, and delta t we are solving for. We're going to add 2.96 on both sides. 2.68 plus 2.96. Then we're going to divide by 9.8 to isolate delta t. Whoops. I had delta t in my head. Divide by 9.8, and that's going to equal to delta t. Sweet, and type that into your calculator, see what we get. That gives you delta t of 6,698 seconds. So 3.2.3, the distance between the hot air balloon and stone B at the instant when stone A strikes the ground. So, there's a few things we're going to have to look at here. So the balloon, which I'll do in red, the balloon's moving upwards at a constant speed of 2 meters per second. Okay? And then what happens is 5 seconds after, so let's call this point when they drop, so that's 200 meters above the ground, right? So this is a distance of 200 meters. And that point there is when they drop ball A. Now stone B is going to be done 5 seconds after ball A drops. So it's going to start moving down. 5 seconds after ball A goes down. So this is ball A, this is ball B, and in red is the balloon. This can be represented as a time of whatever A's t value is, plus 5 seconds. Okay. T plus 5. So because this would just be t, and that's going to be 5 seconds after that. So we're trying to figure out how far the balloon would have gone how far the balloon would have traveled up in that time frame. So if this was t, and this is t plus 5, that time there would be t minus 5. Okay, so we're looking at the distance that the balloon went. So delta y we can say is equal to vi delta t. And delta y is what we're calculating. So it's vi is going to be negative 2.96. No, I said 2, yeah, that's wrong. 2.96, and the delta t, think about it again. We're looking at the distance between the hot air balloon and stone B at the instant when stone A strikes the ground. So if stone A strikes the ground at t, stone B would only strike the ground at t plus 5, which means that we're going to look at t minus 5, the time it takes for stone A to hit the ground, minus the time difference between when we released ball B and ball A. It's a bit complicated, but hopefully I can explain that. It's the best I can explain that. So it's going to be 6,698 minus the 5 seconds of delay between ball A going and ball B. Put that in, put it into your calculator. You get that the ball would have traveled a total displacement of negative 5.03 meters, or 5.03 meters upwards. Okay, so now we're going to look at how far this ball B went. So this is the balloon. Now let's look at ball B. So what do we know about ball B? We actually know the time now, which should be t minus 5. Because at the end it's t plus 5, so in the beginning must be t minus 5. And yeah. And we're trying to find the distance, eh? So I'm just going to use the same equation. Vi delta t plus a half a delta t squared. So the change in that distance there, that we're trying to calculate, the Vi is negative 2.96. Delta t being 6,698 minus 5 plus a half a, which is 9.8, and then 6,698 minus 5 all squared. So that gives us an answer for a hot air balloon traveling. I mean the ball traveling, not my bad, of 9,13 meters. So we're going to take the difference then, not the difference, the sum, because this is up, that's down. So this total distance here, we're going to get that would be 9.13 meters plus 5.03 gives us a total distance of 14,16. So the next question, on the same set of axes, draw position times graph for both the hot air balloon and the stone air from the moment it is dropped until it strikes the ground. So we're using the ground as a zero reference in this question, which means our x-axis is going to be the ground. Our y-axis is going to be the displacement that the thing moves. Now I'm only going to draw a negative side because I took downwards as negative. But let me just draw a positive, just a small positive so it looks nice. This, yeah. So that's going to be delta y, and this would be delta a. So they're both going to start at the same point on the graph. But the difference is that the ball is going to move slightly upwards in the beginning because it has an initial velocity, and it's going to go down at a constant rate. Whereas the balloon is going to move straight up all the time at a constant rate. Remember, up is down because down is positive. So if we draw this graph for the balloon in white, it's going to look something like this. Constant speed is going to move upwards. Now if we drew our stone in blue, it's going to move up for the beginning bit, like so. It's going to reach its maximum height, and then it's going to go downwards. Like that, and it's going to hit the ground. It then may also bounce. I'm just going to draw that for interest's sake. It may also bounce straight up, go up a bit again, then it will go down. And it would continue like that. The bounce is getting less and less because it loses energy in the bounce. And until it stops and doesn't have enough energy to continue bouncing. So in blue we have our stone, and in white we've got hot air balloon. So I decided to choose the negative one because it's harder to draw and they might force you to do negative. Essentially a good way to do a negative graph is to actually just draw a positive one and then turn your paper upside down. Because it's the same thing. Let me show you what I mean. Let's highlight this and somehow invert it. Wow. Look at that. And now if you were to imagine it mirrored, it would be exactly what you want, right? So this is just running in reverse, but that's how it would look like. So you can draw it the right way up and then turn your paper upside down. So it's a nice easy trick you could do. Back around, okay. I just actually want to point out something. Technically, because the ball is not gaining, it's continuously losing speed, not actually going to pass the balloon on its way up. Let me rectify that. This is something I thought of now. The balloon's always moving up at the same speed, right? But the ball is slowing down as it goes up. which means it's going to be more like this. It's not going to pass the white line. It'll start at the white line and then it'll join there like that. So that's a better description of the motion. Let's take a look at question 4, which is normally in the test conservation of linear momentum. So that's what we're probably going to have to use in this question, yeah. So a ball X of mass 10 kilograms is moving eastwards with a velocity of 2 meters per second. It collides elastically, which means that the kinetic energy before is equal to the total kinetic energy after, with another ball Y of mass 2 kilogram was moving with an unknown velocity Vy. And immediately after the collision, ball X comes to rest and ball Y moves eastwards with the kinetic energy of 36 joules. So explain the meaning of the term elastic collision. As I said, the total kinetic energy before collision needs to equal to the total kinetic energy afterwards. Or in other words, the total kinetic energy of the system is conserved. Next up, we need to calculate the value Vy. So, seeing as they just asked us to describe elastic collision, I'm going to use the equation for an elastic collision. That's a nice trick. Typically, if they ask you for a definition, you're going to use the equation of that definition. So, essentially, we're looking at the sum of kinetic energy initially, which needs to equal to the sum of kinetic energy at the end. Okay, so sum of Ek initial equals sum of Ek final. And now let's break this down. So we have the half mx, and then half mx vx squared plus a half my vy squared going to equal to, and this is all initial, going to equal to a half mx vx squared final plus a half my vy squared final. So let's take a look at what we know. So ball X of mass 10 kilograms, let's substitute that in. It's a half times 10. Vx squared, do they tell us? They do. It's moving eastwards at a velocity of 2 meters per second. I can put in that 2 there. Plus our ball Y, which was moving with an unknown velocity. So it is moving, but we don't know what that velocity is. So we can't say it's 0. But we do know its mass, it's 2 kilograms. And it's got some velocity, Vy initial, squared. So this is going to equal to a half. The mass of this ball will stay the same, but its velocity becomes 0. And then the ball Y moves with a kinetic energy, we've been given kinetic energy here, of 36 joules. So I don't actually have to substitute any of that in. I can just say that that is 36, because this is kinetic energy. So now we can get solving. That's going to be 5 times 4, which is 20, plus Vy squared, so 2's cancel, is equal to a half times 2 is 10, but that's a 0, so it's 0, so it equals 36. Vy squared equals 36 minus 20, which is 16. So that means that Vy is equal to 4 meters per second. Now the question is, what direction would it be going in? I'm going to assume it's going to move to the right, but I don't think it's important. Just trying to think where it would be going. Was moving with an unknown velocity. Wait, I lied to you. It needs to stop that ball, right? So it needs to have been moving that way at a pretty fast speed to have stopped it. So it's going to be 4 meters per second left. Alright. Yep. The balls were in contact with each other for 0.1 seconds during the collision. Calculate the magnitude of the force that ball X exerted on ball Y during the collision. So we're going to take a look at that. I'm going to switch my colors around. So 4.3. And calculate the magnitude of the force to ball X. So we're going to use F net. It's equal to the change in momentum over change in time. Change in momentum of ball X on Y. So that's going to be M V final minus V initial over the change in time, which they told us was 0.1. So the mass of ball X is 10 kilograms. Its final velocity was 0, and its initial velocity is 2. So that's going to be 0.1. So negative 20 divided by 0.1 is negative 200 newtons. Now let's read the question again. We need to calculate the force ball X exerted on ball Y. So if it's moving that way, we're going to take the positive answer of this because I'm taking the right as positive. And because of Newton's third law is the reason why we can do this. I'm going to say F net equals 200 newtons on ball Y. So you can definitely have a negative answer with these questions. But then you got to read your question again, see what you have defined as a positive direction. So we took right from the straight from the beginning where I substituted a positive value for the velocity as a positive direction. So then we read our question and we want to know what the ball X exerted on ball Y. It's obviously going to exert a force in this direction, which must be positive. So because of Newton's third law, what I actually did here was calculate Y on X, which would be the other direction. But we wanted X on Y, so all you need to do is flip the sign around and define exactly which ball is going for what. That's not too difficult. Don't have to worry about which values to substitute. Just at the end, think about it carefully, and then you can decide what the right answer should be. They mark both either way. Alright, question 5. Okay, also question 5 is typically your energy question. So they say a 2 kilogram box is released from rest at point P up here, and which is 5 meters above the ground. It slides down a smooth, frictionless curved track PQ. Boom. In the diagram below. And it looks like that after that it becomes a friction full track. I don't know how you would say it. State the principle of conservation of mechanical energy in words. In an isolated system, the total mechanical energy remains constant. So use the principle of conservation of mechanical energy to calculate the speed of the box when it reaches point Q. Okay, that's important. They specifically told us to use this principle, which means we can't use work energy theorem, we can't use equations of motions. We must use the conservation of mechanical energy. So what is the conservation of mechanical energy? Essentially, E mech at A, or let's say P in this case, E mech P needs to equal to E mech at Q. Now mechanical energy is given by U plus EK. and this is all at P, equal to U plus EK at Q. Alright, so we know that the U at P is going to be all the way to the top, and that's mgh, and the EK is going to be 0 because it's not moving. I'm just going to say 0. And then U, as here, is going to be 0 because it's at the bottom, but EK is going to be half mv squared. And that's what we're calculating. We're calculating that velocity. So the mass of this object is 2 kilograms. The gravitational acceleration is always 9.8 on Earth. And the height is 5 meters. Is equal to half times 2 times the velocity squared. We can divide by, we don't have to divide by anything, because that cancels out, which means v squared is equal to that sum there. So it means 2 times 9.8 times 5 is 98. Square root of 98 gives us a velocity of 7 root 2. 7 root 2, yeah, that's right, sorry. Which I'll write quickly as a decimal. It is 9.9 meters per second. Okay, next up. The box passes point Q and moves 10 meters on a rough horizontal surface before striking a barrier at point R at a speed of 4 meters per second. So they've given us the speed at here, over here, at here, 4 meters per second. They've given us the speed over there, and over here we just calculated the speed to be 9.9. So let's see what the question says. Use energy principles to calculate the magnitude of the average frictional force acting on the box as it moves from Q to R. Very important, they said energy principles there. So you can't use equations of motion, but you can use any of the energy equations. So you can use W net equals delta EK, or you could use work done by non-conservative forces. I'm going to use W net equals delta EK. It's the quickest one for this. It's the only force acting on them at that point is friction. And then it's just delta EK. So that's the quickest one to use in this case. So we'll, for 5.3, what's it? Yeah, 5.3. It's back to white. We're going to use W net equals delta EK. This is the work energy theorem also. W net is force, frictional force, times the displacement times cos theta is equal to the change in kinetic energy, which is a half m v final squared minus v initial. So frictional force, do they tell us? Oh, that's what we're calculating. Okay. But they do tell us the distance, which is 10 meters. And cos would be 180 degrees because friction acts in the opposite direction relative to motion. That's going to be half the mass of this object is still 2 kilograms. V final squared is 4 squared minus V initial squared, which we calculated to be 9.9 meters per second. Be 9.9 squared. So essentially, to get our answer, all we need to do is divide by that term. So F is equal to a half times 2. 4 squared is 16 minus 9.9 squared. And so let's do that in my head. Divided by negative 10. Plus 180 is negative 1. So whatever this answer gives us, put it in our calculator. 16 minus 9.9 all squared divided by minus 10. Gives me an answer of 8.201 newtons. Right. So thanks. This would just be part 1 of a part 2. I'm going to stop here for now. Give myself some time to edit. Right. Please check in for part 2. We'll continue with the next few questions, which is going to be our Doppler effect, electrostatics, circuits, generators, and photoelectric effects. Thank you for watching.